Mike, I forgot to record this. Maybe somebody could, if they have good notes, they could post it on discussion board so that Mike can get this.
Okay.
Dang it. I hate when that happens. We'll go back. So at least we're sharing, at least we're recording this part of it. Okay, so in here, what is this asking? What is this inside the box? What is it asking?
Question.
What does it say?
Is it saying that
How is temperature changing with respect to y?
Okay, those of you who've taken my courses before, the very first thing we talk about with the derivative is that we go, that's a question. You could say, how does temperature change with respect to y? Fine. You could say, how does temperature change as y changes? But that's not the best way to describe this time. You'd say, how does the temperature change as
You move from
As an air parcel
you move
goes
as you
south to north.
goes what direction?
South to north.
South to north, right? So how does the temperature change as you go to the north? Now, first of all, do you agree that the temperature change over a distance, what is that called?
gradient.
That is called a gradient. And you will find that we have something called the gradient operator, which we're going to get to. But just so you know, we know what a gradient is in meteorology. Do you agree there's a temperature gradient, change in temperature over a distance?
Yep.
In this case, what is the value, based on this diagram, what is the value inside this box? Now, I'm not looking for a specific value. Remember, if I said dt or dt dy, that's a question. How does the temperature change as you move north? How many answers are there to that question?
A lot.
No. Wrong. You forgot, James. Go back, review your notes from 11:15 because we do this in both classes. How many answers are there to this?
3.
3. What are they?
Oh,
It increases, it decreases, or it stays the
It's
same.
the same.
In this case, what is it doing as I move to the north?
Increases.
It increases. So this is plus. Sorry, I'm freaking out here just for a second, so please ignore the man in the mask. How does the no, what am I saying? Stop. What did you say? Okay, you just messed me up. I hate all of you. What is the temperature doing as I go to the north in this?
Decreasing.
So what's the value inside this box?
Is it negative?
It's negative. That's a horrible negative. But that's the value inside the box is negative. Thank you. God. No wonder I was like, have I just screwed up here? Horrible thought. So if I add them together, if I were to say this is a plus sign, and you can't really call that a negative, you see, because it is negative in there. That would make this getting colder. At that point, this would get colder. So the formula is actually going to say this. It's going to be minus this.
so minus v dt dy, negative dt dy would be it's getting warmer?
Well, yes. No, I'm just talking about a generalized formula. So let me go over here. And I'm going to go the partial of t with respect to t is equal to the total derivative minus the velocity times the temperature gradient. That is the formula. In this case, do you agree that the temperature is getting colder to the north, so the value of dt dy is negative, as Allison finally made my brain work and function. I waited too long to get more coffee. So if this is negative and the wind from the south is positive, then a negative times a negative is positive, and that advection will make this temperature at a point get warmer. Capiche?
Okay. Can you do that one more time for me just so I can make sure I got this written down right?
No, why don't you do it?
All right. So we have the winds moving from the south because it's negative.
No. The winds are moving from the south, so what is the wind? V, it's what?
Winds are moving from the south, so V is negative? Or
That's your problem, James. The winds are moving from the south. It's moving to the north,
oh,
which is
to
a
the north.
positive
Okay.
wind.
Okay.
So you have to think in here, what is V? V is positive. Keep going.
Okay. So then you have the change temperature over Y, which would be over north-south. So it's a negative change in temperature with negative DT
Yeah, because as I go positively to the north, what's the temperature doing?
getting higher or getting lower, sorry.
Getting colder, right? So it's a negative temperature change. So the change in Y is positive, the change in temperature is negative. So negative, this term here is negative, this term here is positive. A negative and a negative is a what?
Positive.
So that means in this case, this term is doing what to my station observation?
It's warming up that point.
Making it warmer, which makes sense, right? You should know that. This is what's happening everywhere by the sun.
Okay.
Okay? Now, if we know that Y is north and south and X is east-west, do you agree that I can generalize this formula into this? And what do you think the X direction wind would be? See, here's something that we haven't told you. This is little v. Little v stands for a wind, or the component of the wind that moves north and south. So what do you think the wind component that moves east and west would be called? What letter do you think I would use?
Is it W?
No, east-west wind?
Is it
Oh,
no? It's a U.
you,
And what was the
okay, you're
temperature change?
using,
Is there any reason we used U instead of W?
Well, here, in your book,
you're using vector notation.
Ah, okay.
go in your book to page 4.
Okay.
Look at equation 1.2. What do we call a wind that goes east-west?
Like Meridiano or one of those?
Now, well, it's one of those, but east-west is what?
Latitude.
Now, look what it says in equation 1.2.
Longitudinal.
Huh?
Zonal velocity.
Okay, so zonal. So a wind that goes from the east or from the west to east, or east-west winds, are zonal. So this is the zonal component of velocity times the zonal temperature gradient minus V, which is the what wind, what component,
Meridional.
meridional, minus, okay, U, V, what's next?
Now it's W.
Now it's W, because W is the vertical wind component, times dt dz. So this is the gradient in temperature in the zonal direction. This is the gradient temperature in the meridional direction. This is the temperature gradient in the vertical direction. Vertical temperature gradient, meridional, zonal temperature gradient. U is the zonal wind. V is the meridional wind. W is the vertical wind. Now,
That's
I'm going-
partial T over the last two, right?
yep. So what I'm going to do now, just to show you how science works, is I'm going to hide all this. I'm going to go over here, and I'm going to go, I want to look at something called the total derivative. And the total derivative, best way to deal with the total derivative is to go to Wikipedia.
Oh, I remember this.
No, I lied. That's horrible. See, this is why I hate math people. Because really, can't you just give me a total derivative, something easier?
That's why math courses are hard. They're taught by professional mathematicians.
There. This one might work. And I'm going to show you how, yeah, here we go. Beautiful. So over here, we're defining the total derivative, the derivative of some function with respect to time, and notice it's little d, equals the partial of that function with respect to time plus the partial of f with respect to x times dx dt. But what's dx dt, folks? Look at equation 1.2 in your book. That's
It's
how
zero.
do I change my location in an x or in a zonal direction, east-west, with respect to time? Isn't that a velocity?
Right.
Plus the change in the function with respect to y times the changing in the y direction, which is a v velocity, plus the w change. So in here, this little bit of stuff, and gosh, gee, I wonder why. If you ever want to find good information, tornado.sanfranciscostateuniversity.edu. This is John Monteverdi, who always has really good information, because I think he must be a really good teacher. I know John personally, he's a good guy, but every time I see anything well written, it's John's notes. Okay, and that's why when you look at all this other stuff on total derivatives, it's like, what the hell? It's so confusing. And you stop losing. I mean, look at the way they've defined things here. It's just brutal, in my opinion. Hopefully, this is my way is a little bit better. I hope. Now, something else I want you to see is sometimes you'll see capital D for the total derivative, which again is John Monteverdi. But if that's the case, that's the same thing as little d. It's just a different notation. Not sure why that is. I think it is because math teachers want to ruin your lives and are causing you great suffering and pain. Okay, so I'm going to go back to where we were, and I'm going to go back to showing this diagram. Does that make some sense to you? So they're just saying all they really did was take that other side, look at this, guys, and bring all these terms onto the other side. Now, those of you with a little bit more advanced stuff, we're going to use the del operator because that's what this is. But we're not going to do that now for this class because I don't need to do this right now. We'll do that in a day or two. Does this make sense here, guys? In
Yeah.
that box. So I'm going to say it once through, and I want to see if any of you can practice. The temperature change with respect to time at a point in the atmosphere is equal to the total change, changes that are going to happen everywhere, minus the zonal wind times the zonal temperature gradient minus the meridional wind times the meridional temperature gradient minus the vertical wind times the vertical temperature gradient. By the way, notice that the vertical temperature gradient is actually nothing more than a lapse rate.
So W dTd or W partial TdZ is the lapse rate.
Well, dTdZ is the lapse rate.
Ah.
You're multiplying the lapse rate times the vertical velocity. I can't tell you how important this concept to fully understand is, because this explains a lot of things about how temperature's changing. When we deal with severe weather, we want to see a lapse rate increasing. Well, the lapse rate increases when there's vertical motion. Like if you took 1115 with me, you would have known that ascending air increases the lapse rate. Well, part of the reason is you're changing the gradient. But we'll talk about that later on.
Okay,
Yeah.
just to make sure I got one thing.
Yeah.
Those negatives too is because the gradient itself is technically negative.
Yes. This,
Okay.
In this diagram, Nick, this
Yeah.
gradient is a negative dTdx. It's getting
Yep.
colder to the north. So that makes sense. So just remember, and we're going to see this when we start dealing with it in terms of vectors. Gradients have a direction. As I travel to the north, in this example, as I travel to the north, it's getting colder. dTdx is negative. Just like if I go up, most of the time, dTdz is negative. As I go up, as I go vertically, the temperature is getting colder. Usually that's the case. Now, one last thing, just because why not, we might as well just tell it. When I deal with something that's this, that word that we described to this is called Eulerian. When I have this, the term that we would put with that is Lagrangian.
Damn it! Where are my colored pencils?
Now, if you read through page 5 in your book, they use those terms. The so-called Eulerian and Lagrangian rates of change are related by the chain rule based on that little thing. So look at top of page 5 if you've got your book up. Do you see that they're missing something? They have how, like, look on the left-hand side of the first equation on page 5. Go ahead, respond. Come on, you all need to do the Pavlovian dog.
That's the question.
All right, Bruce, look at the first term on the left-hand side of the first equation on page 5. Ask me the question.
Where's the T?
Right? You're like, how does change with respect to time? So what they're saying is that there's a gap. You need to put something in there. So what I would do is I go dt, and then I just put t in in the blanks.
Oh, okay.
Well, let me ask you something like this. So here's something. You know what this means? I don't even know if I can draw it well. What is that symbol?
Supposed to be percent?
Supposed to be a percent, right? If I said 70%, do you understand? I'm saying it's really, what that really is doing is it's taking 70 and dividing it by 100. You agree? If I just see a percent, what I really need to say is, oh, that's per 100. That's all it is. It's divide by 100. So when I see this thing on page 5, we call that an operator. It's just we need to do something with it. So you plug in that value. In this case, percentage, it's 70, and here you say T. You could also go dP, dt. How does the pressure change with respect to time? And so all of that stuff is just saying we're going to use this thing called an operator, and we'll be talking about that coming up later. So there's a blank in it because you need to put something in it. Because if you ask the question, how does, and then you're not saying anything. Let me try one more concept just as a meteorological thing. Have you ever seen me in class? Or have you ever seen this symbol?
No.
Okay. Do you remember what mixing ratio is?
Yes.
It's grams per kilogram. Right? Grams of water vapor divided by kilograms. So if I said the mixing ratio is 7 grams per kilogram, the symbol would be this. That's percentage. That's 100th. That's 1,000. So sometimes you may see that the mixing ratio is this. And that just means grams per kilogram, parts per 1,000. That's not super important. If you ever see that, now you know what that is. All right, so let's try. Let's try this. Somebody explain to me this in the box.
Okay, I'll try to explain that, I guess.
All right.
So the derivative at a point is equal to the total derivative minus the zonal winds, the change in zonal winds, the change in meridional winds, dang, and the vertical winds. It's subtracting the change of all those winds from the total change.
Do you know that when I take this, let's see, dTdx.
That's a partial symbol, not a D. I really should write those a bit clearer.
Yeah, I mean, it's partial. So you're going to have to, Allison, you're going to have to be neat with all these things.
Oh.
That's the partial. I'm assuming you've gotten that to be pretty good.
That's
If you go to Word, you can do equation editor. They have the partial symbol. What is this? What would you say U is? Everybody?
Zonal wind.
Oh, and
Zonal wind. What's dTdx? The partial t with respect to x, but what is this?
horizontal T gradient.
Not horizontal. Because now we're doing in 3 dimensions. This is the zonal temperature gradient.
Yeah.
Okay. Zonal wind times gradient. Okay.
It looks like tau.
Yeah, I know that's I'm bad. I'm ashamed of my bad T. How's that? Is that better? So that would be the wind times the gradient. Well, whenever you take the wind times the gradient, you know what that's called?
Convection.
You know what this is called? Oops. You know what that's called? What's this called?
Vertical motion.
Lamps.
Well, it's W is vertical velocity, right? This is the temperature gradient in the vertical or elapse rate. But do we call it advection?
Convection?
Convection.
That's the convective term, right? That's convection. But it's vertical advection. Anybody else want to deal with this, or are we good to go on? Obviously, this is all on video. You can go back. Anyone? Last chance. I'm going to delete.
For advection, that can be both in the X and Y direction.
Correct. One of them would be zonal advection. One of them would be meridional advection.
And for vertical, it's just convection.
It would be what we really refer to.
Yeah.
Okay, so here's what I'm going to do after. That was a lot of work that we did on this one page. So what I'm going to do is this. Oh, no, I'm going to do is erase that and go to arrows. Do you understand? I have a three-dimensional coordinate system. In this case, X, Y, Z. Zonal, meridional, vertical. Then what I'm going to say is I'm going to put an arrow in here. And I want you to imagine that this arrow is sort of like this. And that arrow goes down, goes this way, and goes this way. Does that make sense? Actually, let me go ahead and do this. Might be easier to see. Do you see how this vector is sticking out of the plane?
Mhm.
And it has an X component, a Y component, and an X component, a Y component, and a Z component. X, Y, Z. It's a three-dimensional vector. So this green vector is a combination of air going this way, of air going this way, and of air going this way. If I added this vector plus that vector together, I'd get the real vector. Okay, so what I'm saying is that this vector here, the green, is the actual vector, put a little vector on top, V, capital V. Those small vectors, this is the U component, this is the V component, and this is the W component. So if I add U plus V plus W, I get the total vector. So all I'm doing, U, V, W, zonal, meridional, and vertical. Basically, it's just saying I'm breaking a three-dimensional vector into its two-dimensional or single-dimension structure. I'm breaking it into components.
Three-dimensional, not two.
It's a three-dimensional. I'm breaking it down into its single-dimensional components. The U, the V, and the W component.
Three-dimensional vector breaking into its two-dimensional components?
No, three-dimensional vector breaking it down into its single-dimensional components.
Gotcha.
Zonal is a single dimension, X. Y is a single dimension, in meridional and W is single component vertical. That's what that means. Okay. How's that working for you guys now? That's kind of important that you understand these derivatives and what that means, because I think here's what I am pretty good at. I remember what it was like for me always to be confused. I was always confused in math class. I did stuff, I figured out stuff, I did all the associations, and I was angry because I'm like, why can't you say this better? And I thought, why do I get good at math after doing it for a couple of years? Why can't you teach me it from the beginning so that I can learn it in the future? And that was the purpose of intermediate, was to sit there and say, hey, you don't have to have calculus. I can teach you what you need to know to understand physically what's going on. Use the physical atmosphere to discuss the calculus. And I hope that's what we can get across in this idea, is that I can use that to get a better understanding of math. Then math class is just doing all the exceptions. The basics of calculus are pretty fun. So that's the purpose of this.
Certainly a lot more fun than I remember math in high school.
I like math. I hate math class.
I
Okay.
think I'm learning that more every day.
Okay, so good. Now let's go on. Let's go back. We're going to go back to here to e to the x. So what does that graph look like? Oh, that's a really big. What is e to the x? E is do you guys know what e is?
Transcendental.
I'm going to go on a little tangent here. Exponential function. Yeah, this is probably going to be good enough. So let's do this. Move you guys over here. Read this to me. Somebody else read it out loud. Jacob, would you?
We're at.
Starting with overview.
Okay. The exponential function arises whenever a quantity grows or decays at a rate proportional to its current value. One such situation is continuously compounded interest. And it was this observation that led Jacob Bernoulli in 1683 to the number, whatever that is.
Okay, so let's think about this for a second. 1 plus, let's imagine that n is 1. So if I plug in 1, and I start with that, and then I add 1 to it, I get 1 plus 1 is 2 to the first power is 2. What if I plug in 2? 1 plus a half is 1.5, but I'm taking it to the second power. So I'm squaring 1.5. What if I took 1 plus 1/3, but I took it to the third power? If you keep going for a long time, you're going to start coming to a number. Okay, and what is the number? Let's see if it's in here. This is so freaky. Look at all this stuff that people have put in there.
2 point.
What is
Zero.
the value of E?
2.7.
If you do that, you get 2.7182 blah, 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 blah. And
You got one
that's
digit.
it is. It is a irrational number. It goes on forever, I think. And it just keeps going, and it's called the exponential, which is really fascinating. And so Jacob Bernoulli is the one who said, gosh, this is how interest works. If I lend some stuff out and I grow exponentially, so anytime we say our interest is growing exponentially, we're talking about a factor of E. But that's where it comes out. There is a book. And I just want to recommend a really fun, great reading. It's called The Simpsons and Their Mathematical Secrets. Love this book. It is so interesting. It's not all online, is it? No. I don't think it's on. No, it's not. Anyway, this book is all about The Simpsons. How many of you watched The Simpsons?
Used to.
Okay.
Used to a
The
lot.
Simpsons, in their team of writers, have like a couple of mathematicians, a couple of computer scientists. We're talking with PhDs in computer science or mathematics.
Did you just say a couple of?
A couple of, Allison, not a couple mathematicians, couple math guys. Couple of. Oh, don't get me started. So anyway, they have these mathematicians and computer science people, and it's really amazing how many different things they have. Like they have a baseball team there called the Isotopes, and they'll go, guess today's attendance, and they'll have the 4 numbers of how many people they think are attending. And it's really not that funny, except what happens is people who know math go, wait, there's a clue in there. And each of those 4 numbers has a mathematical significance. It's a super prime, or it's a square of something. It's an amazing thing. And this book talks about all those inside jokes of mathematics. And they have a really good explanation of where the exponential number comes from. And it's a wonderfully fun book. I learned a lot about math by reading this book. And it's all about things that you see in The Simpsons. So here's a
Donut.
the donut, which is what is that, ellipsoid? No, it's there's a name for that. I can't remember what it is. So if you want to get that book, it's a lot of fun. It's a fun read, and it's really like mind-blowing humans thing of mathematics. Okay, so we're looking at an exponential function. Which in E is just a number, 2.718 to a power. Well, to a power is pretty straightforward, isn't it? It's just whatever x is, or it's this to some x. So what does that exponential function plot to? I guess I should have. And is this what you wrote in here? No, that's 2 to the x. Where's e to the x? Actually, can't you do this? E. I think I can just do that in here. And you get the exponential function. So what happens is e to the 0th power, obviously any number to the 0th is 1. And then as the numbers get greater than 1, you're taking e to higher powers, and it's going to grow very quickly exponentially. When you get numbers that are less than 0, e to a negative number does what to it?
Bigger negative.
It no, e to the
Like
negative number,
Becomes a
Which is 0.
No
fraction.
negative.
it's the reciprocal, right? It's e to 1 over e to the x. So the bigger the number, negative, the closer to 0 you're going to become. So this graph becomes asymptotic as approaches this 0 as you go negative. but it grows exponentially, way off the chart here to the top. So the question is, what is the slope doing? Well, way down low, the slope is near 0. And then as we get closer, it becomes 1 when x is 0, and then the slope grows exponentially big. Well, what function says when I take the slope at really, really small x values, it's close to 0, it's 1 when it's at 0, and it gets really, really big? And the answer is, well, the damn same function. The derivative of e to the x is e to the x. So if I go in here and I say, let's go here, and I'll write with my pencil, and I go, the derivative of e to the x with respect to x is equal to e to the x. The easiest thing that you can do. Does that make sense to you? The exponential function grows in its tangent, the slope of the tangent, the same way that the function itself does. So what's this one?
E to the 2x.
How do you know? Like, how would you prove that? If you don't, some of you don't have the math, you don't have the calculus background to know this derivative. Some of you have the calculus background and you know that derivative. But what if you forgot? Could you figure it out again? Isn't this nothing more than e to the x times e to the x?
Yep.
And then what can I use to figure this out?
Chain rule.
What? The product rule.
Product rule.
So that would be
Yeah.
e to the x times the derivative of e to the x with respect to x plus the same thing. So can I just simplify life by saying 2?
Mm-hmm.
But what's the derivative of e to the x?
E to the x.
E to the x. But what's e to the x times e to the x?
E to the 2x.
So it's e to the 2x. So generalizing, what I'm going to say is that the derivative of e to anything is nothing more than n times, sorry, and really what you want to think, because you're a pattern recognizer. If you're a meteorologist, you better be. All you're doing is you're taking this guy in front and keeping everything else the same.
I guess you could look at it too as you take the derivative of what's in the x or in the exponent, and then times the original e to the nx.
And what's the derivative of nx? It's just n dx. I'll put this over there. Anytime you have a constant, you bring that out. So
yep.
Hopefully that's a fun one. So let's do this. Let's skip to these guys. Oops, not what I wanted. Why do I have a big black mark there? What the heck? What am I doing? Oh, you know what it is? I'm in draw in Word. I don't want to be draw on in Word.
Ah!
How did I get it to draw in Word?
It's like one of those things you accidentally hit a key on your keyboard that activates like 15 functions you didn't know existed.
I'll go back to select. I think. There we go. Okay, that's what I want to do. So what I really want to do is these last two functions. And so rather than draw this, because it's a pain in the butt, I'm going to go, and I'm just going to type in sine x. And luckily the sine x is pretty straightforward. This is probably the better one that we can look at. The sine function, this is not a good one. I don't want this one. I want this one. The sine function is a what?
Sine wave.
It is a sine wave, right? That's what we do. It is a wave. Do you guys remember what sine is defined as? And I hope you know this. I hope everybody in this class knows this. What is sine defined as?
The distance. It has to do something with distance with within a circle, right?
You could think of it that way, but there's an easier thing. What
Okay.
word do I need to know? What am I going to write down? Allison?
Bueller.
Bueller? What word am I going to write down here?
I know I'm a victim of the American education system.
SOHCAHTOA.
Is everybody familiar with this word?
No.
Yep.
Hmm.
Bruce, you're not
You mean the opposite over hypotenuse?
Oh, in trigonometric terms.
Yeah. So,
Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent.
so here's the angle. Here's the opposite. Here's the adjacent. Here's the hypotenuse. That in this angle, whatever that angle is, the sine of this angle is the opposite over the hypotenuse. It's a ratio of these triangles. Now, what you were talking about, Nick, is when I look at a circle, right? There's my circle. I can draw pretty good circles, I think. And I have a pen that draws circles. And I take something like this. What I'm saying is I can draw in here a right triangle inside that circle where the hypotenuse is always the radius of the circle. So when I'm looking at that, I'm looking at the size of this angle. Well, if the size of this angle is 0 degrees, what does the opposite side become?
0.
0, and the hypotenuse is the same as the adjacent. So the sine, the sine of 0 degrees is going to be 0. Well, the cosine is the adjacent side over the hypotenuse, and if this angle is 0, then the adjacent side is the same as the hypotenuse. Do you understand what I'm saying?
Yes.
I'm basically taking this. I'm taking this side, and I'm making it smaller and smaller angle until when the angle is 0, they're the same. Hypotenuse and adjacent the same, and there's no opposite side. So the sine, the cosine of 0 degrees is 1. So if you haven't had trig ever, that's kind of what we're talking about. But does everybody know SOHCAHTOA? James, have you done
I
that?
am familiar with SOHCAHTOA. It's been a hot minute, but I do remember it.
Okay, well then that's kind of why we have to have some prerequisites so that we know something about that. So this is the sine function. And the sine function is basically saying at pi over 2, which is not, this is the same thing as saying 90 degrees. The sine function is maximized at 1. And then just based on circles and what quadrants of circles we're in, over here it's going to be -1. So what we're saying is that the sine function does what? I want you to use the correct word. What is the sine function doing?
Oscillates.
That's the correct word. The sine function oscillates between +1 and -1. It also goes to 0, or you're basically saying I've got one complete wave every 360 degrees, every 2 pi. So when I draw a sine wave, like any of these are sine waves, I'm saying they're periodic. They keep repeating. Like, look at this one up here. They repeat every 2 pi. But it oscillates between +1 and -1. It's positive at 90 degrees, it's negative at -90 degrees, and it's 0 at 0. The cosine does the same thing, it's just offset by a little bit. I guess I should write.
Modern furniture and design construction. Oh boy.
Yeah. The cosine function is +1 at 0, because we've said this, and it does the same thing. But it oscillates just the way a sine function oscillates. It's just offset by a little. So here's something that's interesting. Here's, in green is the sine function, in blue is the cosine function. So they're like two waves that are offset by how much?
Pi.
They're out of
One.
phase by 90 degrees.
By
over
90
2.
degrees, pi over 2. Right? So it's not quite pi, it's pi over 2. Or just simply 90 degrees. Here's another example of that. So if you think of these, if you think of anything as waves, waves can be offset when we talk about waves that are baroclinic, they're amplifying waves, they're going to be a result of temperature advection. So the isotherm field and the pressure field are offset by 90 degrees, and you get this perfect amplifying wave. Anyway, we use them a lot. But here's the question. What is the slope of the sine wave when at 0? And the answer is 1.
1.
What is the slope here?
0.
0.
What is the slope here?
1.
1.
Not 1.
-1.
-1.
Negative
Yeah.
1. What's the slope here?
0.
0.
0. Okay, so the slope is 1. That's here on the cosine. The slope is 0. That's there. Slope is -1. That's there. And the slope is 0. That's there. So as we find out, it's a pretty simple relationship that the derivative of the sine function, hold on. With respect to x is nothing more than the cosine. It's periodic, it oscillates. Okay, let's look at the other way around. What is the value of the slope of the cosine?
0.
0. Oh, that's great. What's the value here of the slope?
Negative.
-1.
-1. Oh, but the sine is 1, so it's the derivative of cosine of x with respect to x is going to be the negative of sine x. Now, I have a horrible memory when it comes to lists. Like, I can't remember I have a garden, I've got flowers, I have no idea what the flowers are. I love my flowers, but I don't know what they are. And I can never remember if the derivative of sine is cosine or the derivative of sine is negative cosine. I don't remember those things. I forget them all the time. But what I do is I can recreate this graph on this page and know that the derivative of sine is cosine, the derivative of cosine is negative sine. Okay, what that leaves us with, and it's time to go, is we want to deal with this one, and this natural log function is a pain. There are some definite problems with trying to do the derivative of that. So that's what we'll talk about next week. So what I'd like you to do is there is a worksheet on our page, which is the note taking, and it's got some derivatives to work out. So I'd like you to try to do that. Let's see if I can get to it quick.
Paul, instead of finding the sine and cosine waves on a graph, you could probably just Google a list of derivatives.
Well, you could, but if you're taking a test and you have to have it memorized, that's probably not the best thing to do.
No, probably not.
So here's your worksheet. Sorry that I have to do this. Here's your worksheet. Here's stuff on logarithms and derivatives. What I'd like you to do is go do this stuff. So I would say try to get everything up to this point. You have an entire weekend to work on this. But these are just understanding how to do derivatives, how to look at notation, how to figure out what's going on. And then at the beginning of this worksheet are some other things. Try to work on through some of that. That's just reading your book. Try to start working on that. But really hit the derivatives and the logarithms. And then we'll deal with this again on Thursday, or next Tuesday.
So up to the point where, up to the derivative section, you said?
Yes.
All right.
That'll just be something that you can end up doing. Fair enough?
Fair enough.
Fair enough.
Okay. And Allison, what's your friend's name again?
Emily. What?
Hi, Emily.
Hi.
Hope you enjoy this. We'll see you guys.
So next Thursday.
You'll see you next Thursday, and the rest of you will see on Tuesday, and this will be up there. And if anybody can put on our discussion board maybe a copy of the first set of their notes, that would be awesome, so I can give it to Mike, because I feel bad that I forgot to record. Okay, guys. Wonderful weekend. See you later.
Hey, you too, Paul. Take
See you
care,
later.
everyone.
Bye-bye.